Hello. Today I'm going to explain how to solve the longest common substring problem in linear time using suffix trees. So my outline will go like this: an overview of the longest common substring problem, an introduction to the suffix trees, and how are we gonna solve the problem using suffix trees. And then I will explain Newconnen's algorithm to construct suffix trees in linear time. So let's start with an overview of the longest common substring problem. So given an input, two strings x and y of length n, and we need the output to be the longest common substring of x and y. For example, if x equal ABA and y equal ABB, then we need the output to be AB. And this problem can be solved in O of n squared using dynamic programming, which I will not explain here just for the sake of the time. So the problem is, can we solve this longest common substring problem in linear time or big O of n time? And it turns out that this is possible if we use suffix trees. So what's a suffix tree? So basically, a suffix tree is a data structure containing all the suffixes of a given text. And suffix trees have many useful applications because they allow fast implementations of many string operations. So how we build a suffix tree? So if we have a string, like for example, the word banana, and we usually use this $sign just to indicate when our string ends. So we start by getting the suffixes and building the suffix tree, starting from the longest suffix to the next, to the second longest, and so on, by keeping the edges compressed. And so every path from the root node to a leaf represent a suffix. And this number right here in the leaf node is the index of this suffix in the original string. So for example, the suffix banana has its leaf node labeled with 0, and this 0 is the index of the suffix banana in the original string. So the only problem with building suffix trees in this way is that it takes a running time of O of n squared. So in a few, we will see how we can improve this to build the suffix tree in big O of n. Before going into the details of how to build the suffix tree in linear time, let's see how are we gonna solve the longest common substring problem using suffix tree. So given a first string x equal xab xa, and the second string y equal bab xb, and we want to find the longest common substring of these two strings. So the first step is that we will concatenate the two strings x and y in a single string s, and we will just put this hash and $signs to indicate the end of each string. And from this concatenated string, the index of the string x is 0, and it has a length of 5 characters. So indices of its suffixes would be 0, 1, 2, 3, and 4. Similarly, for y, it starts with index 6, and it has a length of 6. So the indices of its suffixes would be 6, 7, 8, 9, 10, and 11. So what we do is that after concatenating the string, we build a suffix tree for this concatenated string right here. And we, as I said before, we label the leaf nodes with the index. And then using a bottom-up fashion, each leaf node will convey to its parent from which string does it belong. So for example, here, the suffix a hash has an index of 1, and we know that the index 1 belongs to the string x. So, okay, the suffix a will convey that it came from string x to its parent node. Similarly, the suffix $, has the index of 7, and we know that index 7 belongs to the string y. So this edge right here will convey this information to its parent and says, okay, I'm coming from string y. And we will keep doing this in bottom-up fashion until reaching the root node. And then to get the longest common substring, we will use depth first traversal, and the path label from the root node to the deepest node marked as xy will give us the longest common substring of x and y. So here, this path right here marked in red is the longest common, gives us the longest common substring of x and y, which is ABX. And as we saw, all the operations that we have done here are linear time operations. So getting the longest common substring from the suffix tree is a linear time operation of n. So let's now return to the problem of how to build the suffix tree in linear time. So we will use an algorithm called Yukonin's algorithm. This algorithm is a linear time algorithm. It works in steps from left to right. There is one step for every character of the string. So basically, we will take each character of the string, we will do some operations on it, apply some rules until our tree is built. And it's a type of an online algorithm, which means that it deals with the string as a stream of characters, processing each character one by one without any prior knowledge of the whole string. So let's see a simple example to explain better how the Yukonin's algorithm works. So we have a string x, s equals ABC. These are the indices of its suffixes. So we start by creating the root node. And at step 1, we are processing the first character A. So we insert a new edge and label it A. And it ends with a leaf node, and we label it with 0, where 0 is the index in the string where we can find this suffix. So if we went to index 0 in this string, we'll find suffix A. But actually, this is how edges in Yukonin's algorithms are presented. So instead of writing the actual character on the edge, they represented as 2 characters. The first character is the start index of the character that we're trying to represent. So in this example, A has the start index of 0, and this hash represents the stop position, which is in our example 1, which means after the first character A. So basically it's the same thing. It's just another way of representation they use. And the reason why they do this is just to make the edges compressed or have like a constant size for any edge. So for example, if we have a really long set of characters, we don't have to consume too much space writing all of these characters. We just represent them using 2 characters. So next step, step 2, our current position is 2, so we are now processing the character B. So at each step, our goal is to insert all the suffixes up to the current position. So we do this by first expanding the existing edge. We had just one edge A. So we expanded by appending the character B to it, and then inserting a new edge B. And here in this representation, this happens automatically. So this hash character is automatically incremented to indicate the current stop position. So for example, here, the start index is 0. 0 in the original string is A. The hash value is automatically incremented to represent the current position, the current stop position. So it's now so it now becomes 2 instead of 1, which means it will end after the second character after the AB. So it's the same thing. And here the second edge starts with 1, position 1, ends at position 2. So it's still the same thing. Step 3, our current position is 3. We are processing the character C. Same thing, we start by appending this new character C to all of our existing edges. And then we insert a new edge with the character C. And similarly, this is just the compressed representation of the same thing. So as we saw here, the amount of work at every step was just a constant time of 1, because all the existing edges are updated automatically by incrementing the hash value, which represents the stop position of the current edge. And even inserting the new edge with the final character is also a constant time operation. So if we have a string of length n, we will need a running time of O of n to build this suffix. But before jumping into this conclusion, let's take another example, because like in the previous example, it worked so nicely just because the string was very simple. It didn't have any repetitions. So let's just look to a more realistic example right here. So the string S is now ABC, ABX, ABCD. It starts with ABC, just like in the previous example. So essentially the first 3 steps are the same. So I just started from step 3. Our current position is 3. We have the same tree that we ended with in our previous example. So let's now move on to step 4. At step 4, our current position is 4. So we are processing this character A. So as usual, we insert all suffixes up to the current position. So we start by appending A to all of the existing edges. And the second step is to insert A at the root, as we used to do. But before we do this, let me just introduce to you 2 variables. These 2 variables have always been there since the beginning of the example 1, but we haven't used them so far. So the first variable is called the active point, and it's a triple vector consisting of an active node, active edge, and the active length. By default, the active node is the root node, the active edge is null, and the active length is 0. The second variable is the remainder, which is an integer, indicating how many new suffixes we need to insert. And by default, it's equal to 1, and it gets incremented at the beginning of each step, and it gets decremented if during the step a new suffix is successfully inserted at any new edge. I know the exact meaning of these 2 will become clear soon. Just bear with me. So now let's get back to step 4. Our current position is 4. We were trying to insert the suffix a, but if we turn back here to our tree, we will find that suffix a is already inserted in the tree. So what we do in that case is that if we find the suffix already inserted in the tree, we don't change anything about the structure of the tree, but we just update the active point to be root A1. This means that now the active point is somewhere in the middle of the outgoing edge of the root node that starts with the character A and specifically after position 1 on that edge. And this is like our first observation. So when the final suffix that we are trying to insert is already found in the tree, we do nothing about the tree, but we just update the active point. So at step 5, our current position is 5. Since we just started a new step, our remainder is incremented by 1, it becomes 2. Our active point from the previous step is root A1. We are now processing this character B, and because our remainder is 2, the remainder tells us how many suffixes do we need to insert in the current step. So we now need to insert the 2 final suffixes from the current position. Our current position is B, so the 2 final suffixes will be AB and B. So we start by appending B like what we used to do. We start by appending the character B to all of the existing edges. And the second step is that we will try to insert B. So now comes the role of the active point. So the active point tells us exactly where are we gonna insert this new suffix or this new character that we are trying to insert. So we go to the active point and it tells us, okay, go to the outgoing edge from the root node, the edge that starts with character A, specifically after the first character. So this is the active point. It tells us to insert the new character B here. So when we try to insert this new character B, we will find that it already exists there. So as we did in the previous step, we do nothing about the structure of the tree and we just update the active point to be root A2. So it now it will now point to this position right here after the B. So moving to step 6, new step, we have to increment the remainder. Remainder becomes 3. Our current position is 6. Our active point from the previous step is root A2. We are now processing the character X. So we start by appending X to all of the existing edges. And then because of the remainder is 3, which means that we have to insert the final 3 suffixes from the current position, 6. So we have to insert ABX, BX, and X. And the active point tells us exactly where AB ends, or in other terms, where do we need to insert X. So we will jump directly to this position and check whether X is already there or not. And based on that, we will insert X, or we will just update the active node like what we used to do. So now we go to the active point the outgoing edge from the root node, the edge starting with the character B, specifically after the second character, the position 2. So we search for X, okay, X is not there. Okay, great. So we need to insert X at this point. But before, we can just insert X in the middle of this edge. So what we do is that we split the edge, insert an internal node that points to the suffix that to be inserted, and it also points to the previously existing like set of characters. Okay, so we just inserted the new suffix X. So according to the rules of the remainder, it has to be decremented by 1, so it becomes 2 instead of 3. And now we need to insert the remaining suffix bx. But before we do that, we will need to update the active point. We will update the active point according to this rule number 1. So this rule tells us that if we split an edge, which we just did, and the active node was the root node, and yes, this is our case here, we have to change the active point so that the active node remains as the root node, but the active edge becomes the first character of the suffix that we are trying to insert in this current step, and the active length is decremented by 1. So in this current step, we are trying to insert the suffix bx. So the first character of the suffix bx is b. So this will be the active edge, and the active length will be decremented by 1. So here we are. The active point is changed to root b1. And this indicates that the next insert has to be made at this bcabx edge behind the first character, behind the b. And we are inserting bx. So we will go to this position and we will check whether x is already present or not. If it was present, we would just end the current step. We would have left the whole tree as it is, but x is not present. So now again, we will insert x by first splitting this edge and inserting an internal node in which the internal node will point to the new suffix x and also to the existing set of characters cabx. And again, according to the rule, since we did a split in the edge, we now have to update the active point in which the active node remains as the root node. The active edge becomes the first character of the suffix that we are trying to insert, which is b, and the active length is again decremented by 1, so it becomes 0. And since we inserted a new edge right here, so we also have to decrement the remainder from 2, it becomes 1. And so this leads us to rule number 2, which says if we split an edge and insert a new node, and it's not the first node inserted during the current step, so we have to connect the previously inserted node and the new node through a special pointer called a suffix link. So we're still at step 6. In this step 6, yes, we did 2 splits. One time we have split this edge that was previously ABCABX, and now we split BCABX. So our rule is saying if we did 2 splits in the same step, we have to connect the previously created internal node with the newly created internal node through a pointer, and we call this pointer a suffix link. So now we are still at step 6. Our current position is 6. We have the remainder 1. So this means we still need to insert one last suffix, and our active point, which tells us exactly where would this suffix be inserted, is root B0. And since the active length component of the active point has fallen to 0, so this means that the final insert will be made to the root directly. Okay, and since there isn't any outgoing edges at the root node starting with X, so we just insert a new edge and label it as X. And now we are done with step 6. Moving to step 7, our current position is 7. Our remainder that was 0 in the previous step, but incremented since we just started a new step. So it became 1. And the active point is root B0. We are now processing the character A. As usual, we start by appending the new character A to all of the leaf nodes. And then we try to insert the new character to the active point. The active point is now the root, and we will find that we have an outgoing edge at the root node that starts with A. So we don't change anything about the tree, and we just update the active point to be root A1. And we are done with this step. We go to step 8. Our current position is 8. Again, the remainder is incremented since we just started a new step. Our active point is root A1. We are now processing the character B. We start by appending the character B to all of the leaf nodes, as usual. And then we attempt to insert a new character B to the active point, which is root A1. Root A1, and we find that it's already there. So we do nothing about the tree. We just update the active point to be root B2. But after we updated the active point, that it became root B2. So it's now right here at the end of this edge. So so we are falling off this edge. So if this case happens, we have to update the active point to be this internal node that the active edge is pointing to. So it becomes this node, node 1. So now the active point becomes node 1, null and 0. So we'll move to step 9. The remainder gets incremented because it's a new step. The active point is node 1. And this new node, null 0. We are processing character C. So we start by appending the new character C to all the leaf edges. And next we go to the active point to see if we can insert C. So we go to node 1, and we find that we have an outgoing edge that has that starts with character C. So we do nothing about the tree, and we just update the active point to be node 1, C1. And we move to the next step, step 10. Our current position is 10. The remainder again gets incremented by 1. So it becomes 4. Our active point is node 1, C1. We are processing character D, so we start by appending the new character D to all of the leaf edges. And then we go to the active point to see if we can insert D or not. So the active point is node 1, which is this node. Specifically, the edge starting with the character C after the first position. We will not find D. So now we have to insert D by first splitting this edge and inserting an internal node that points to D and also points to the previously existing set of characters. And yeah, so this is after the split. The active node from which the split was initiated is this node right here marked in red. And this okay, now we have our third and final rule, which says after splitting an edge from an active node that is not the root node, which yes, this was the case. We just split an edge from an active node and it wasn't the root node. We follow the suffix link going out of that node, if there was any, and reset to the active node to the node it points to. If there wasn't any suffix links, then we set the active node to the root, the active edge, and the active length remain unchanged. So let's see in our example. So here we just split an edge and we split it from an active node. This node right here, the red node, was our active node. So what we have to follow the suffix link going out of that node and reset the active node to the node it points to. So now we will have a new active node, which is this node right here. Okay, this is the case if we have a suffix link. And yes, in this case, we are lucky we have a suffix link. If not, if we didn't have a suffix link, we would just have set the active node to be the root node. And in both cases, we don't change anything about the active edge or the active length. So now after applying rule 3, we have this active point as node 2, C1. And this is what I'm mentioning as node 2, this one here marked in red. And since we made a successful insert, we now decrement the remainder by 1, so it becomes 3 instead of 4. Our active point is node C1. Our next suffix that we are trying to insert in this step is BCD. And we do this we insert this suffix by simply inserting the final character D at the current active point. So we'll go to the active point, node 2, the edge starting with the character C, specifically after the first character. And we'll see if D already exists or not. And right here, node 2, C after the first character, okay, D is not there. So we will have to again split this edge to insert D. Split this edge, create an internal node insert an edge labeled as D. Okay, here it is. And since we just successfully inserted a new suffix, the remainder gets decremented by 1. So it becomes 2 instead of 3. The active point is still node to C1. But now, since we made a split from a node that is an active node, we have to follow rule 3 to reset the active point. And here, this new active node has no suffix link to. So according to rule 3, we will reset the active node to be the root node, but we will not change anything about the active edge or the active length. So the active point is now reset to root C1. And so this means that the next insert will be on the outgoing edge of the root node, whose labels start with the character C behind the first character. Which will be right here after this first character. So this will cause another split to insert the character D, another internal node point to the newly inserted edge D, and at the same time the previously inserted set of characters. A remainder will be again decremented because we successfully inserted a new suffix. And since this step involved the creation of new internal node, we will follow, and in the same step, in step 2, we already had the same exact situation. Another edge was split and another internal node was created. So according to rule number 2, we have to connect the previously created internal node with the currently or with the just created internal node with a pointer and call it a suffix link. We are still in step 10. The current position is 10. Our remainder is 1. Our active point is root C1. And since the active node is now the root node, we use rule number 1 to update the active point to be root D0. And this means that the final insert will be made directly to the root with creating this new edge D. And finally, after this step, the remainder will be 0 because we just inserted a new node and our algorithm is done. So let's jump to some conclusions. So as we saw in each step, we just moved this hash value forward by 1 position. And this automatically updates all the leaf nodes, or it appends the new character to all of the leaf nodes in constant O of 1 time. But it doesn't deal with any suffixes remaining from previous steps and with that one final character of the current step. The remainder variable tells us exactly how many additional inserts or additional suffixes we need to make, and each insert of those is done in constant time of 1, since the active point tells us exactly where to go and we need to add only one single character at the active point. Why do we only add a single character at the active point, because even if the suffix consists of several characters, the other characters are contained implicitly within this active point, or otherwise the active point wouldn't be there. After each insert, we decrement the remainder and follow the suffix link if there is any. And if not, we go to the root, which was our rule 3. If we are at the root already, we modify the active point using rule 1. And in any case, any of those rules takes constant time of 1. And if during one of these inserts, we find the character we want to insert already there, like it was the case many times, we didn't do anything about the tree. We just updated the active point, even if the remainder was bigger than 0. The reason is that any insert that remains will be suffixes of the one we just tried to make. Hence, they are all implicit in the current tree. And the fact that the remainder is bigger than 0 makes sure that we will eventually deal with these remaining suffixes in the next steps. Okay, so in our previous example, we ended the algorithm because we found the remainder greater than 0. So what if it was the case that the remainder was greater than 0? This will be the case whenever the end of the text is a substring that occurred somewhere before. In that case, that's why I said when I started explaining that most of these algorithms use the $sign to indicate like the end of the string. So what's the complexity of the entire algorithm? If we have a text of n characters or a string of n characters, there obviously we've done n steps, or n+1 to be specific if we added the $sign. And in each step, we either do nothing other than updating some variables, or we make remainder inserts. And in any of these cases, we will take a constant time of 1. And since the remainder indicates how many times we have done nothing in previous steps, and this is decremented for every insert that we make, so the total number of times we do something is exactly n or n+1. Hence, the total complexity is big O of n. And that's how we prove how can we solve the longest common substring problem in linear time using suffix. Thank you.